Welcome all. My name is Dr. Hrishikesh Sharma, and today we will be starting the Module 1 first lecture of the course Blast and Impact Resistant Structures. So, in the Module 1, we will be providing you with the introduction, general introduction about the extreme events, and we will be giving into an overview how we are going to analyze the system, what are the different signatures of the extreme loadings, that is the blast and impact loading, what are the different design philosophies, what are the tools that we are going to use, and at the end of the day, what is the whole overview that we are going to present to you. So, let us start with the slides. So, in part 1, we will be introducing the extreme events. In part 2, we will be talking about the blast load. In part 3, we will be talking about the impact loads. And in part 4, we will be dealing with the simulating blast and impact loads and its effects on the structure. So, part 1. So, let us try to understand what are extreme events. So, extreme events are high energy occurrence events which involve short time durations and high loading rate. So, remember one thing, whenever we talk about the extreme events, there will be two signatures. One will be its high loading magnitude and its short duration. So, that is how in general we quantify the extreme loads. And when this type of loading occurs, there is a rapid deformation in the structure, and it may lead to a catastrophic failure in the structure. So, some of the examples are explosions, vehicle crashes. So, as I said earlier, the characteristics of the extreme events are they are rare occurrence. Okay. So, in day to day life, we are not going to see every day the occurrence of the extreme events, but when they occur, they lead to major repercussions. They have a low probability of occurrence, they have low chances of occurrence, but when they occur, they have a high impact on the infrastructure as well as our day to day life. And due to its very high loading magnitude and very short duration and the amount of failure that it can cause, it poses a severe design challenge. They defy the normal design methods, they defy the normal design consideration, and it involves special consideration whenever we are dealing with this extreme type of events. So, classifications of events. So, events can be classified into two parts: natural events and man-made events. Natural events we normally deal in our day to day life, such as earthquakes, tsunamis, hurricanes, floods, landslides, wildfires. But when we talk about extreme events can be man-made events dealing with the explosions, impacts, or some industrial accidents. So, industrial accidents, we are familiar with the Chernobyl accidents, impacts whenever an aircraft hits the building, such as what happened in our 9/11 event, explosions during a wartime. The current wartime also we are seeing different type of bombardments that are occurring in the different cities. So, this type of things are classified as the extreme events, and due to their severity, it calls for different design considerations that are different from the normal design considerations. So, what happens is that the extreme event is a multifaceted event. The structure is subjected to very high loading and it is very susceptible to damage and collapse. So, right now when we deal with the normal events, we are dealing with the crack type of event, we are dealing with the serviceability type of events, but in extreme type of events, we normally deal with the severe damage and collapse type of events. There is a very significant amount of non-structural damages as well. There is a disruption in the functioning of any infrastructure. There is a downtime. Let us say if our electric power substation is subjected to a missile impact, then it will face a severe downtime. And the amount of disaster that will be caused, the amount of failure that will be caused, so it will require a lot of time to rebuild it. So, disruption and downtime are the hallmark of any extreme events. Economic loss, there is a severe economic loss if our highways break down, if our facilities such as hospitals or our business center break down, there is a breakdown in the data server infrastructure. So, this all things accounts for a severe economic loss, and it will also lead to a cascading failure of the infrastructure. So, let us say an extreme event occurs and it destroys a highway. So, not only it has destroyed that particular highway, it has also destroyed the entire supply chain line, and when the supply chain line collapses, it will affect the other parts of the economy. So there will be always a cascading failure amounting from the extreme events. So that's why today's need of the day is to analyze these events, be prepared for these events, and design our infrastructure facilities so that we can deal with this type of extreme events, and our structures and our different other infrastructure facilities are able to withstand this type of extreme events. Let's now look into some historical perspective where we will see that this type of events has occurred. When we talk about the blast scenarios, some of the very well known examples that we see is the 1917 Halifax explosion. So here what happened was the devastating explosion was caused, and it led to the first initiation of different safety regulations. Then one of the most famous blast explosion is the Oklahoma City bombing, where terrorist attack leads to the heightened security measures. Of course, 9/11 attacks we all know, and that changed the whole global scenario, be it aviation, be it building inspection, be it building safety, be it building design and analysis methods that we are currently following. So these catastrophic events reshaped the entire emergency protocols, the security infrastructure, the structural community's outlook towards these extreme events. Other events also occurred in different type of other infrastructures, such as Beirut port explosion. So this triggered the safety standards for the storage and transportation of the hazardous materials. So this also inculcated the petroleum ministry and the other ministries dealing with the oil and natural gas. So each and every aspect of our infrastructure is vulnerable to blast and impact explosions, and we have to design for them. Engineering relevance. Why we need to study these extreme events? As I am saying from the previous slides, extreme events, though they have a low probability, but they are high consequence events. They are relevant from the angle of maintaining human safety, infrastructure integrity, and the economic consequences. We have to be always prepared for the extreme events, and now in this current scenarios, we are all aware that our infrastructure are very vulnerable with this type of threats, and we need to be prepared and design for this type of threats. So we need to design safety critical structures. Okay. For example, our defense installations, our automotive installations, our aerospace installations, our nuclear installations, our IT installations, they all need to be considered carefully, and they have to be designed to resist the blast and impact type of extreme events. So in automotive engineering, where we always see a certain type of impact event, so they need to be crashworthiness, meaning we need to maximize the occupant protection by controlling the energy absorption mechanism and the deformation that is happening in the automotive sectors. Okay, for example, car, vans, and the other things where every day thousands of passengers or goods are being transported. So we need to protect them with any type of impact that is occurring in the highway as well as in the railway sector. In civil engineering structures, so as I am telling earlier, all the civil infrastructures need to be made resilient against blast and impact type of extreme events. Aerospace structures, where we are always faced with the impact from the debris, where impact from the bird hit, so and some other hypervelocity impacts also we are always dealing with. So they lead to a localized catastrophic failure, and as we have seen, when an aircraft gets damaged, it has a very low chance of surviving. So our aircraft industry needs to be made resilient with this type of impact type of events. Military and defense installations always at the forefront of this type of events. So they are the most targeted installations for this extreme type of events, and we need to design our structures, our armors, our vehicles, so that this type of extreme events they can sustain. Even in case of personal protection systems such as full body armor, they need to be designed to withstand the blast and impact type of events. As we saw in the previous slides, our offshore industries are also susceptible to this type of extreme events. There might be a sympathetic blast due to the fire occurring in the high petroleum things. So they need to be designed for this type of explosions also. So what are the different hallmarks that we see in this type of blast events? There is a high strain rate event effects, there is a very fast stress wave propagation in the structures, the inertia and the dynamic effects are engaged very fast, and there are certain characteristic failure modes that are different from our normal failure modes. So some examples of the crash or some examples of this extreme events we see as a small car crash that goes and hits some sort of installations such as walls, the fenders or any other roadside vehicles. Blast events that occurs in the buildings may be due to cylinder explosion or may be due to some small of terrorist explosion. So that causes a failure mechanism. Other type of impact event that we see is missile impacting our nuclear containment structure or bunkers. So what happens there is a high speed projectile slams into the reinforced or steel plate, and in certain rare cases like in case of bunker busters, what happens is that after the hit of this high speed projectile, there is a mechanism, there is a bomb mechanism which ignites and there is a secondary explosion. So this type of things also needs to be dealt with when we are designing our bunkers or our IT protection installations. So there are some inertia driven responses also after a shock load has been applied. So if it is a very low intensity shock load also, the secondary vibration effects comes into picture. So the structure will keep on vibrating, and due to the low rate fatigue or in some cases high rate fatigue, the structure will eventually collapse. So we need to be prepared and design for all these scenarios. Some of the characteristic of the blast loading or this extreme type of loading is that the rate of loading is very severe. So if we talk about our normal dynamic loads such as earthquake load or wind load, they come into our medium range of loading. So the strain rate is very low. When we are talking about blast and impact events, surface explosions, they come into very high strain rate events. So what happens with this very rapid loading is that our structure stiffens. Okay. So due to the stiffening, the strength, there is a significant increase in the strength, but with this significant increase in the strength, the ductility also goes down. So our normal conventional practices that we use for normal design, that is not applicable here. So we have to redesign our materials. We have to analyze our materials again and get their characteristic values. We cannot use our old material things. So that's how this type of events also warrants a very deep study into the material characterization also. Most of the times the extreme events are very rapid events. So they account for a very severe lookout into the dynamic analysis, and their dynamic analysis is marked with the very big chunk into the inertial effects. So we will be dealing into those kind of approximations also. So as the course progresses, we will be looking into the dynamic analysis of the structures. A full scale dynamic analysis will be covering single degree of freedom analysis, and we will be covering multiple degree of freedom analysis also. So the extreme events has also they also warrant a different signature as far as the stress wave propagation comes into picture. So in the stress waves, what happens is that a travelling mechanical disturbance is generated when a sudden load or impact is applied to the material. What it does is that it carries a momentum and energy throughout the structure. Due to the sudden loading, a pulse wave is generated that travels throughout the structure, and this duration is often very small as compared to the natural period of the structure. So what is happening is that the structure is not going to behave uniformly. It develops a locally damaged mechanisms, and that rapidly propagates through the entire structure. There is a reflection in the material creating wave fronts, and if there is a multiple interference from different sources, there might be an amplification and causing failure of the entire structure. So, now we are dealing with the frequency and the severity of the extreme events. So, now we will talk about the risk assessment of the extreme events. As I told earlier, the extreme events are rare, but severe incidents. They have a very low chance of occurrence, but when they occur, they have a signature of high magnitude and a very short time duration. They are very catastrophic events. The risk associated with those events are very high, because the impact that those events cause are very severe. So, this type of events, though they are occurring the probability of occurrence of them is very low, but they require continuous monitoring, and it will also cause minor inconvenience as far as the monitoring goes. So, we look into the probability versus consequence chart of the different type of events. So, as you can see, earthquake, it has a low probability occurrence also, but consequence is low also. The extreme events, they have a low probability occurrence, but the consequence is very high. So, we will have to be always ready, and we will need careful planning, will need careful mechanism in order to deal with this type of structures. Engineering challenges in the design for extreme events. The loads are unpredictable, they have very high magnitude as well as very short time duration, and the uncertainty associated in predicting this type of events is very high. This type of events are rapidly deployable, they occur very rapidly to a structure. So, the structural response is also very different. The material undergoes a very non-linear behavior, there is a plastic deformation, and there is a sudden failure in the material behavior. This type of events also impacts our structure depending upon affecting its overall structural integrity and overall structural stability. These events can occur on their own, or they might occur in combination with the other extreme type of events. So, when 2 or 3 type of extreme events are combined, then again it requires careful planning, analysis and design. We are looking into the risk analysis of the extreme events. First of all, what we need to do is that we need to assess the potential threat, we need to identify the threat. For example, we need to identify the threat that will be caused by a missile explosion event or a bomb type of event that is kept in a truck or somewhere. Then we need to assess how vulnerable our structural system or any other infrastructure system that is susceptible to this type of events are. Then we need to analyze the consequences, like when this event occurs or when this event is triggered by a third party, then what are the different consequences, what will be, how much damage that it will be causing. Then we need to quantify the risk that due to this damage our infrastructure facilities, the hamper in the infrastructure facilities, the event in the whole supply chain, how much it is occurring. And then we need to come into the acceptable risk thresholds. So, how much risk is an acceptable risk, how much damage is acceptable whenever this type of event occurs, and how quickly we can rebuild or reinforce our systems. So, these are the risk management studies that goes hand in hand when we are dealing with any type of extreme type of events. After that, we have our risk reduction strategies also. Recovery, how fast we can recover the affected installations. Redundancy, so we should always ensure alternate paths, be it a structural system where there are all redundant systems inbuilt into a structure, our highway network where we have alternate paths, our any other hospital or any other infrastructures where we have multiple hospitals which needs to, where we can alternatively schedule the patients, or our IT backup clusters where if one system failure occurs, the other system can kick in. Same is true for our power infrastructure where we have the multiple backups. So, we have to ensure an alternate load path. Protection measures, the design of the structures, we need to augment the strength of the structures, the strength of the already inbuilt structure infrastructures so that they can resist the extreme events to their best extent capacity. Prevention, that reduce the risk, reducing the probability of occurrence of those type of events, meaning we have to design our safety standards, our mitigation methodologies so that this type of events do not occur. And mitigation, reducing the hazard severities, that is also comes into the acceptable risk thresholds. So this type of careful planning, meticulous and careful planning needs to be dealt with whenever we are dealing with our extreme type of loading events. So as we can see, this whole thing does not only box down to the designing of the structure or analyzing of the structure, but it also encompasses the risk analysis processes, the mitigation steps, and the risk reduction strategies. So there are different realms that we have to deal with when we are dealing with this type of extreme events as a whole. Now we will talk about the design process for the extreme events. First, we have to assess the risk and the threat arising out of these extreme events. We will have to identify the potential risks and threats. After that, we need to determine our performance criteria. Nowadays, performance based engineering is coming into picture. So our performance based engineering is different from our conventional design methods. In our conventional design method, what used to happen is that we used to identify one performance level. We used to have only one performance level. Let us say for our conventional design, we will have a performance level where my structure is always in the serviceability limit. So what we used to do is that for all the structure, no matter what its usage is, we always used to define the same serviceability limit for all types of structure. So what used to happen was some structure used to be over designed, some structure came to be over designed. So now we are looking into a performance based design, where depending upon the usage of the structure, depending upon the requirement, depending upon the importance of the structure, we define different types of performance level and associate it with each type of structure. So each structure has a unique signature on how it needs to perform given certain amount of threat. So the performance based engineering is coming into picture. So the categorization of each structure into its perfect performance level is also a necessity. After that, we need to initiate the conceptual design development. We need to create the initial design concepts, meaning we need to approximate the structure, the real life structure. We need to approximate it using some mathematical formulation, either single degree of freedom approximations, multiple degree of freedom approximations, finite element simulations, or as the case may be. After that, we need to adopt or we need to apply the threats either in combination or one by one to the given system that we have mathematically made and calculated responses. After we have calculated the responses needs to be checked, and depending upon the performance level, if it is meeting the requirement, it is okay, or if it is not meeting the requirements, then we need to again optimize the structure so that the given performance requirement is met. So it ensures that whatever was the design criteria, they are meeting with the structure is serving its performance level, and the amount of loading that particular extreme event was causing on the structure is minimal. So the design process for extreme events follows this logical pattern encompassing the risk assessment. So each stage builds on the previous one with iterations if required necessary to finish the whole design process. So this is the philosophy that we are going to see in this whole course. So we were talking about the different performance levels. So in the performance level, what we do is that we establish the damage level. So if let us say a structure is serving a lot of people, or it is of very high importance, or the usage of this structure has to be ensured for different type of scenarios, then we start from a minimal damage, then we assign a minimal damage to this structure. As the usability or performance of the structure varies, we assign different other damage level to this particular structure. So different type of damage levels are, let us say, life safety, where significant damage is allowed in the structure, but the safe evacuation of the people inside the structure should be ensured. The next level in this damage level is the controlled failure, where we ensure that we are predicting the damage mechanism. So, the structure is de-evolving depending upon the damage mechanism whatever we have envisaged. And lastly, the catastrophic damage is acceptable in the structure. When we look into the mitigation of this type of structure, so minimal damage will have zero mitigation, immediate occupancy structures, minor damage repairs are required, it serves minor damage and it can be restored very easily, and the fully functional capacity is restored. Collapse prevention, there is severe damage but there is no collapse. So, the risk associated with this structure is more, but we need not repair it. And catastrophic damage, even the structure is sacrificed, it has served its purpose. So, different performance level correspond to different degrees of acceptable damages have to be defined, and they have to be assigned to different types of structure. For extreme event, we often accept more damage than for normal design considerations. We always focus on preventing catastrophic failure rather than maintaining the functionality. Performance objectives depend upon the usage of the structure. We also need to define the different performance objective like life safety, that is the ensuring the safety of the occupants, asset protection, the physical assets, for example, the disk in the data center or ammunitions in the army installations, they are protected, continuity of the operation, maintaining an uninterrupted operations such as in the electrical power substations in hospitals, sometimes a balanced objective like all the three objectives that has been dealt earlier, like safety of occupants, maintaining physical assets, maintaining uninterrupted supply. Those three things also can be combined in one, and a balanced objective can be established from all those three also. And in some cases there is a client specific requirements, such that in nuclear containment structure or some personal bunkers, there are different client based requirements that needs to be dealt with. So, performance objective, that is an emerging field where we are trying to achieve the requirement based on the functionality of the structure. Life safety, though it is always paramount, but the other objectives like asset protection and operational continuity are also becoming of paramount importance nowadays. And of course, sometimes dealing with the client specific requirements also comes into picture. So, we nowadays what we are trying to establish is that we are trying to establish a balance between all these objectives and design a structure so that we achieve a set performance objective. So, today I will stop here and we will continue from tomorrow the next class. Thank you.